Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. There's a common suggestion in our society that the two most difficult subjects to master are brain surgery and rocket science. Well, today we're going to talk about rocket science. Brain surgery can wait for another day. My guest today is Dr. Eric Besnard. Dr. Besnard is a professor of mechanical and aerospace engineering. Welcome, Eric, and thank you for joining us on Talking Points.
Thank you.
Well, we're going to talk about the future of space travel, space exploration, and space tourism. But before we take a look into the future, we need to take a little bit of a look at history about 45 years ago or so. I remember back in the summer of 1969 when Neil Armstrong took that proverbial giant leap for mankind and put the first human foot on the lunar surface. Back in those days, I was playing Little League Baseball. So that gives you some idea how long ago it was that we started manned missions to the moon. And we continued until about 1972. Actually, I think December of 72 was the last flight, Apollo 17. And at that time, most people were absolutely certain that we'd be landing on Mars by now, probably multiple times by now. But it didn't happen. We lost the momentum. Why did we lose the momentum for manned spaceflight?
Well, I think there's multiple factors, and the big one is cost and interest in the public probably dwindled a little bit, and there were those other aspects that came into play, like the Vietnam War. And I think, for these kinds of programs, you need a lot of money, and Congress, as a result, went and did not fund it to the level that was needed for this manned level of flight to continue throughout those years.
And it seemed like we had other priorities, as you mentioned, and those priorities didn't involve manned space flight, certainly not to Mars. We knew that would take effort and time and engineering skill and so on. And people have used that as sort of an argument against doing it now. They say it takes a lot of money, it takes a lot of engineering resources, maybe we could use that on something else, we have so many other problems. But why should we explore distant planets? What's the purpose in doing that?
Well, when you look at planets and actually exploration in general, this is kind of who we are. We are a species that likes to explore. We went and explored, looked for a route to, not a route to India. That's how we discovered America. You look at, before that, the Tahitians, they found and discovered Hawaii. And it goes back all the way to our roots in Africa. So we're explorers. That's the desire, the human desire. Then there is the survival aspect, which is we want to be able to survive. And on the survival side, well, what happened some 65 million years ago, 10-kilometer diameter asteroid hit the Earth. And a lot of scientists attribute or contribute, or at least certainly associate that with the extension of the dinosaurs. So we certainly don't want to be there. And then longer scale, I realize it's a little bit different now, but 2.8 billion years from now, the sun will not be able to sustain life on Earth. So those are the things where, we're doomed at some point, and so we have to decide. We need to first be a multi-planet species and then multi-solar system type species at some point if we want to survive.
And a lot of people don't realize that there were actually a lot of scientific benefits to society that we were able to transfer the technology from the Apollo program to applications here on Earth that have been very beneficial. What are some examples of those scientific advantages?
On the technology side, there's a lot of little things that we don't recognize or appreciate, but there's some things like advanced materials. I'll just take the example of Teflon-coated fiberglass. It's used for football field, for example, covers, very high strength, low weight. There's solar cells. A lot of the solar energy that we rely on find its roots back in the space programs. We're users of the space program in one way or another. Our GPS is all relying on those satellites. So there's the Apollo program, there's a space program, there's all that technology that, frankly, I think we take for granted. We don't realize it's there. There's the other big benefit, I think, of the program was, when that was the first time we went farther than right outside of the atmosphere on the moon program, the Apollo program, when they saw that little blue planet and realized how fragile it is. And so that's a phase where, you know, they recognized it then, kind of disappeared. Nowadays we're coming back with the impact on the environment. That's a big thing that we realize, and that's a child of the Apollo. You can look at it that way. And then I think there's all these other non-space. It inspired a whole generation to study science and technology, and led to a lot of other industries that, frankly, you know, they may have come around at some point, but Apollo program really helped in doing that. And so that was a big benefit back then, and we have the benefits of those things today.
So just to recap, you mentioned materials technology, you talked about communications, satellites, even probably cellular phone and cellular technology benefited from all of that. Correct. Space exploration.
Yes, certainly.
Okay, well let's talk about Mars, since Mars does seem to be the next target, assuming that we don't go back to the moon first, but Mars is the target, and is it really the only realistic target out there at this time? Well,
Mars and the moon are kind of the two best places for us to be able to go for several reasons. Some are environmental, in the sense of it's not too cold, it's colder. Certainly in both places you have temperature extremes, but it's doable from that standpoint. It's not an environment that, okay, we cannot breathe there, but we're not going to die if we bring our own equipment. You look at Venus compared to that, is not a friendly place. And then there's some gravity on both places. Mars has an atmosphere, nowhere as thick as what it is here on Earth, about 1%. But still, we might be able to do something with that atmosphere, and atmosphere protects us from some of the radiation, not all of it, but some of it. So Mars, I think, is the near-term target. And then also the second big element to that is one where we can go there in a reasonable amount of time. You're looking at, you know, six plus months to get there using the kind of technologies we have access today. So those are reasonable values to be able to make those transportation or those travels.
And you mentioned that Venus is not a hospitable place to be. Why is that?
It's toxic gases and very, very hot. So even hardware that we've sent on the surface, the Russians, I think, sent something on the surface, and it only lasted for a few minutes. So very, very difficult, harsh environment. You could be up in 50, 60 kilometer altitude, like the city in the sky that you have in Star Wars, to be able to have a friendlier space closer to what we're accustomed to here on Earth.
All right, so we're talking about Mars, and there are some advantages to being on Mars. People have talked about colonizing Mars because it is a hospitable planet, and it is something that we could reach within 6 months, I guess. So what about the possibility of colonization of Mars? Does that seem realistic? And what is realistic in terms of getting to Mars with a manned mission within the next, say, 30 years?
Well, I think there's two levels there. We can go, certainly. We have all the technology to be able to go to Mars. I think, do you want to do a round trip? Do you want to colonize? There are major technical advantages to colonizing. If you go there and colonize, then and you stay there, one-way trips are a lot cheaper from a propulsion and so on standpoint. And then that means now you're going to bring supplies on a regular basis. And frankly, the advantage you would have if you colonize it that way, then its funding will have to be there. So that's, to me, I look at it as one of the big benefits, is that political advantage of a one-way trip. Well, you have these people, and you have to be able to help them get to the point where maybe at some point they'll be self-sustaining.
So we have an investment if we do it that way.
I think so.
What are some obstacles that we need to overcome in order to have successful ventures to Mars?
I think on the technical side, the obstacles are, I would say, call it more challenging than obstacles, because they're quite doable. We're talking about long travels in space, so we said 6 months. And the environment is a little bit harsher than it is in low Earth orbit from a radiation standpoint, but scientists have looked at it. There's research, a lot of research going on to try and characterize that and improve things. But scientists are all saying, like, oh, okay, you should be able to do it. It would increase the risks of cancer for those astronauts by a little bit, but still very low percentage. So that's one of the big ones. And then the other one is the lack of gravity for that period of the trip. But we have astronauts that have stayed on there for much longer.
And what about bone density issues and diet and that sort of thing?
Yeah, so all those are related to the microgravity or lack of gravity during the trip. There's means of producing some micro or some gravity during the trip, but even without gravity, like what we have today with the astronauts on the International Space Station, that possibility is there, and they've stayed much longer than the 6 months that you're looking at. And there's gravity on the surface of Mars, not a full Earth gravity, but it's significant. So.
Well, we actually have some slides right now of the International Space Station, and so if we can take a look at those right now, we see the first slide is an image of Scott Kelly, who's been in space for a long time. How long has he been in space?
Well, on this last trip here is, I think, around over 200 days, and cumulative, I think he has the record with over 380 days, and he's got another several months to go to complete this one mission that he's doing right now, which will be a year.
So he's proving that we can send a mission to Mars by being in space that long.
At least from the microgravity side. In low Earth orbit, we're protected by our magnetosphere from a lot of the damaging radiation, not all of it, but a lot of it we're protected. So that's the part that we're not addressing in these flights.
Okay, before we go to our break, we've got a few more slides to take a look at from the space station. Let's go to the next one. The next slide shows an Aurora effect from the International Space Station. What is an Aurora effect?
Well, I was just mentioning the magnetosphere. So that's the fact that Earth has a magnetic field which expands outside of the Earth and interacts with the Sun's magnetic field. And you have those charged particles that go along the magnetic field lines. And when they have a lot of energy, they go and they follow the magnetic lines, which then hit at the North Pole, interact with the upper atmosphere, and create those beautiful auroras that we're familiar with. So that's one of those that you see here.
Let's go to the next slide. And this is a shot, again, from the International Space Station. There we're seeing a tropical storm. That tropical storm that you're seeing, that swirling cloud formation in the Gulf of Mexico, that's contained within the Earth's atmosphere.
Correct. Yes.
And so the space station is about 250 miles up, or 400 kilometers. Let's go to the next slide. And this is an even better shot of a hurricane that's forming in the Caribbean, I believe. So this is a kind of imagery we can use to analyze hurricanes, but you were mentioning to me earlier that we have even better capability of getting photography of hurricanes and weather systems. How does that work?
Well, I think a lot of the weather satellites actually is sitting a little bit, quite a bit further out at geosynchronous orbit. And then you combine this with these kinds of data from low Earth orbit, and then you measure, this is what we call the visible, the things that you and I see, but there's also radar images that you see. And so combine a lot of those observations to be able to make those weather predictions. And then they also fly in those airplanes into those hurricanes.
Okay, and on that note, we have run out of time for this segment, so we will go to the break now. And when we come back, we'll take a look at some more images, and we'll talk about space tourism. Stay with us.
Ever heard of the world's most amazing toy? Uber sticks? I mean, check it out. The Eiffel Tower, the Golden Gate Bridge, cars, and robots are all amazing feats created by mechanical engineers. You could become a part of this creative field with a degree from Cal State Long Beach.
Hello and welcome back to Talking Points. I'm Dave Kelly. My guest today is Dr. Eric Besnard. He's a professor of mechanical and aerospace engineering. And Eric, before we went to the break, we were talking about the possibility of space tourism, and so we're going to talk about that now. When we talk about space tourism, we're really talking about taking normal citizens up into space who pay a fee, and it's a pretty hefty fee, of course, as you would imagine. And they would be able to go about 62 miles above the Earth, which is 100 kilometers, and they would be able to experience some effects of space travel. What would those effects be, and why would someone want to do this?
Well, first of all, they're normal citizens, the difference being they're rich normal citizens, right? But yeah, the point is they would be able to experience the so-called zero-G, so there'd be a trajectory that allows to feel that, oh, you're in outside of first of all, you're going to be outside of the atmosphere, so you see the stars, you see the curvature of Earth, you see Earth with the blue color, and you're in that zero-G environment for a few minutes, 5-6 minutes only, but still you're there for that period of time.
Okay, when I said normal citizens, you're right. Normal citizens that happen to have a lot of money in the bank who can afford this, because the typical flight is going to be about $250,000 for that 6 minutes of zero gravity adventure. And the flight lasts, I guess, about an hour. Is there going to have to be any kind of special training that they're going to need, and do they have to have a rigorous physical for this?
I think, you know, each so-called galactic airline, if you will will have some of that training and some physical. I think in the case of, for example, Virgin Galactic, they're looking at trying to minimize the amount of special medical condition required, so that it's really going to be open to as many people as possible.
And you mentioned Virgin Galactic. They're one of the players in this effort to develop space tourism. Who else is involved in this?
Yeah, as you said, Virgin Galactic is the most, I think, probably advanced and most visible. The other big one who's doing things more under the radar, if you will, that's Blue Origins, and Amazon's Jeff Bezos is the one behind Blue Origin, who has been funding Blue Origin for quite a few years, and they've taken some significant steps in the direction. They have a different configuration for their spacecraft, but I think out of all the others, they're the most credible.
All right, and we happen to have a photo of you, which we're going to look at right now. We have a photo of you standing in front of what's called Spaceship One, which has a relationship with Virgin Galactic, but this is Spaceship One. And this particular aircraft or spacecraft won what was called the Xprize for experimenting with suborbital tourism. What exactly was the Xprize, and why did this spacecraft win that award?
So the Xprize was a $10 million prize modeled after the Orteig Prize, which was Charles Lindbergh won that way back with the Spirit of St. Louis crossing the Atlantic. So that was the model, to be able to have a prize to instill that desire for private enterprise to demonstrate within a few days the capability of launching and recovering the equivalent of 3 people with the same craft, and being able to do that. And Spaceship One was the first one to do that in late 2004. So this picture was right after out here in Mojave.
And from what I understand, the provisions were you had to make 2 space flights within 2 weeks of each other, and you had to maintain at least 80% of the original materials from the first flight into the second flight. So they were able to do that. But Virgin Galactic is very much invested in this effort, and they created a Spaceship Two, which unfortunately crashed in the desert about a year ago, Halloween of 2014. And we happen to have a video right now where they explain the re-entry process with what they call the feather design of this aircraft. So let's take a look at that videotape right now.
Hi everyone, it's Virgin Galactic here with a quick explainer video about our re-entry system, the feather. Now, when most people think about rocket science, they tend to think about how hard it is to blast up off of the surface of the Earth. You know, you need a lot of speed, a lot of energy to slip the bonds of gravity and to make it out into outer space. But of course, physics tells us that every bit of energy that you put into the vehicle, you got to get back out of the vehicle when you want to turn around and come back home. If you're moving really, really fast on the way back up, you're going to be moving fast on the way back down. If you look at the history of human spaceflight, you can see that people have found a couple of different ways to solve this challenge, a few different ways to come back from space and safely land here on the surface of the Earth. Broadly speaking, you can divide them into 2 categories. There's vehicles with wings and things that look like capsules. Things with wings are really gentle to fly on. They can gracefully dive back into the atmosphere, slipping in and exactly the right angle so that the astronauts on board the vehicle get a nice, smooth ride that doesn't have too many G-forces. There's not that much acceleration going on. They also have the advantage that they can come to land very precisely on a known point on the ground. You know, before one of the flights of NASA's Space Shuttle orbiters, you could say with confidence that the vehicle is going to land right here, right on the Space Shuttle landing facility at Kennedy Space Center. You could probably nail it down to within just a few feet.
And Eric, as we saw in the video, it comes into a nice gliding landing there, and it's a reusable spacecraft. That's really the issue here, is reusable spacecraft. We started that with the shuttle, but we found out that the shuttle required 19,000 engineers to work on the next launch, and actually quite a bit of money. And I guess NASA decided that it was just as expensive to prepare the shuttle program for the next launch as it was to just rent out space from the Russians. Why was that?
Well, I think the challenge there was about sending people up there and the cost associated with being able to do that. And if you want to be able to have your own system, your own service, you need to be able to develop it, and it doesn't develop overnight. And the cost, as you said, the cost of shuttle was over $500 million per launch. And so the budget going into this just did not allow to spend the time and money to be able to develop the other one in parallel. So that's what we're doing now, NASA's doing now, is investing into manned space to be able to have our own, the US's own capability to be able to launch astronauts.
All right, and so we were looking at Virgin Galactic and the feather design for the landing and re-entry. Let's take a look at some additional images from Virgin Galactic of that particular Spaceship Two type of craft. We've got the launch craft for the Spaceship Two. We've got the, I guess it's the double fuselage craft. Tell us about this a little bit.
Well, basically it's an airplane. The first stage of the launch system is an airplane which takes the spaceship up to around 40,000 feet, drops it, and then they fire the engine and go into space with the Spaceship One, or Spaceship Two in this case, the one that's in the middle, that's hanging in the middle there.
Okay, let's go to the next slide, and there's the rear view of it on the runway there. Let's go ahead and show the next slide as well. All right, and there it's in flight. So you can see how that Spaceship Two is attached, and let's go to the next slide. More images of it in flight. And if we go to the next slide, I think we're going to see it detaching. How does it actually detach? How does that work?
So all it is a simple hook mechanism. They release it, and the spaceship just drops. And then right after it drops, that's when they turn on the rocket engine.
Okay, let's go to the next slide. And there we see the engine obviously flaring. So the engine has to come on pretty quickly.
Yes, within a matter of a couple seconds. Not even maybe, I forget the exact timing, but very, very fast.
Okay, and then we go to the next slide. All right, and there we see the moon in the background. So this will fly at optimal height somewhere around 100 kilometers or 62 miles above the Earth.
A little bit over, yes.
Okay, and that will give the space tourists the chance to get that view and that experience of zero gravity.
Yes, and I think like on the order of a few minutes, they'll be up there for that fun experience.
Okay, and let's go to the next slide. And there we see the launch craft, the double fuselage launch craft. It's detached and it's on its way home. Let's go to the next slide. And there we see Spaceship Two. What's happening with Spaceship Two there?
So after, when it comes back, it opens its feather mechanism and then comes back in at controlling the speed to avoid accelerating too much on the descent. And then once it gets to proper conditions, then it goes back into the standard glide mode, and then glides back to the port, which is what we see here on the screen.
Okay, all right, and then let's go to the next slide. And this is the last slide in this sequence. So there we see the double fuselage craft on the ground. It's already come back down, and that's how it works with Virgin Galactic. So Eric, as we talk about this space tourism, we need to talk about the risks for a moment, because if you climb Mount Everest now, and many people are doing it these days, the risk or the failure rate is 1%. So in other words, you have a 99% chance of coming back alive. What about with rocket launches? Are we there yet?
Well, and if you look at the statistics, it's around 95% for all systems. And a big part of that is unmanned systems. You look at Space Shuttle. A Space Shuttle, 2 failures out of 135. That's 98.5% approximately. And I think people would argue that's still too many failures. And there's one big advantage on the suborbital flight. It's a lot easier to do those kinds of suborbital flights, put a lot of more, we call an engineering margin in a system, than it is for orbital flight. So I think to get over the 99-point-something%, and I'd argue you're going to want, the public is going to want, the FAA is going to want well over 99.9% reliability in those systems. So I think we can do that on suborbital because the margins are there.
And unfortunately, we've run out of time. But I want to thank you for being here today. And thank you for joining us for this edition of Talking Points. Join us again soon for the next episode. Until then, I'm Dave Kelly. Have a nice day.